Our very first question is, what are the basics of querying row by row, and what might I need to do if I have to look at multiple rows at once? What we're going to do in this question is we're going to look at some of the basics of the SQL select statement. We're gonna use that as a launching point to talk about the intuition behind how the database people think, because it's going to appear more and more so very different than the extremely dynamic universe in which software programmers operate. But we'll start with the most basic. And the most basic thing that I could do in SQL is I could select single expressions. In fact, every time I'm working with my Postgres or MariaDB or XDB or whatever tool I'm using, and I want to figure out, is this thing on? I select just a common expression. I select one. And you can see I can compute that. And I can select any mathematical operation, select 1 plus 1. And you can see it's giving a name to this column, but the name that it's trying to figure out does not quite sure what to do. So I could even give this column an alias. I can say, oh, select 1 plus 1 and call the column that results from this 2. I could select multiple columns, 1 plus 1, 2 times 2, and 3 raised to the third power. And I could say, call that column RV0, RV1, and RV2. Great. I could even, if I'm using Postgres, select multiple rows. One of the implicit things that I showed you was, oh, you can select one column, you can select multiple columns. But what if I want to select multiple rows? Here's the thing. SQL is orientated around its own conceptual basis, and that basis is largely something slightly similar to the relational algebra. But if we think about something like pandas as being a tool for index-aligned in-memory operations on index-aligned one-dimensional data sets, homogeneous data sets, what SQL is about is manipulations of tuple spaces. And when you see each row in my result, that's actually, you can consider it like a tuple space. You consider that a single tuple value, a single record value. It is, in fact, possible in some of our modern tools to select multiple rows at once. Historically, this was not possible because it was outside of the framework of how the SQL designers were thinking at the time. But just like I can use values in an insert statement, I can select star from values, and here you can see I get multiple rows. It's kind of interesting. We'll later see how this might be useful for something actually practical. Another thing that I might discover is there's all these functions in SQL. Before I get to that, another thing that I might discover is my select statement is superpowered. It's supercharged with the ability to not only select the data for me to view, but also to select that data into another table. And so here I select that data into a temporary table. And you could think multiple select statements in a row could populate a temporary table, and that's another way that you could perhaps try and get a result set that has multiple independent rows. If we think about this as being each row a tuple, and we think about what a tuple means in Python, it means kind of like a record, a structure. What we can think is this is our way to retrieve multiple distinct entities with 2 facets per entity, X and Y, and 3 entities in total. Now, going beyond that, one thing that we may discover is our SQL dialect has a lot of functions, and some of these functions can do some very interesting things. Unnest gives you the ability to take array data and turn that into multiple rows. And this actually comes up quite a bit when you're working with things like materialized views and you want to join things in some complex ways. But I'll leave it here. You can see for the most part, it's not that natural for me to select multiple rows in a single expression. Usually I'm selecting multiple columns and performing column level computations. And so, rather than go too far into the details of unnest and how we can alias this table with a name, I want to show you, and we can do quite a bit with unnest as well. We can do something akin to a zip, so we can unnest 2 arrays side by side to get something like this. And you can think this is why it starts to come up with materialized views. Oftentimes you're constructing new data from existing data, especially if that materialized view wants to, for example, give a column that has JSON encoded data that's going to be fed to a REST API. You might need to start joining data together and basically zipping it up. But what I want to talk about beyond all of that is that when we're working within these tools, we're largely working on, at least with the select statement, operations that are performed row by row where you can perform computations on these. And here you can see I can actually select compound values in Postgres. Here, each one of these values that I'm selecting, this is a single select statement, so it's going to get you one, and it's a single select on a single expression. So it's going to get you one independent row, and within that, each one of these is a compound value with the pieces associated with it. If I did something like this, select row from, and then I unnested something, like I unnested an array like this, you can see I get 2 rows. But there seems to be, and each one of those has 2 values, but there seems to be this intuition, this force that's kind of telling me the select statement operates row by row. And it's kind of clumsy or kind of difficult or requires special syntax or special functions in order for me to retrieve multiple rows at the same time unless my resulting table has multiple rows in a single expression. Or in other words, to allow me to operate on multiple rows simultaneously. Let's think about the distinction between SQL and pandas. If I have a pandas data frame, it's very common within that pandas data frame for me to do operations on that data frame and for those operations to refer to other portions of that data frame, to refer to the 0th row or the last row, because pandas is an in-memory tool. Whereas SQL is all about data sets that are not necessarily small enough to fit into memory and being very judicious about how much you load into memory at any one time. And so it's very difficult in SQL to say, give me the first and last row of the table. There's not necessarily a built-in ordering to how the table is stored. And it's not easy to say, oh, while you're performing this operation, divide that by the last value you can see. Here, I have a little bit of code that's going to generate some data that will give us a sense for what we can do with some SQL queries and some advanced select statements. And so I have some game data. I'm playing a game like NetHack or Moria or Rogue, and I have a bunch of players who are different professions and who are different species and some monsters that they fight and they defeat when they're going through the depths of the dungeon. And it's going to generate quite a bit of data here. It's going to be some data representing each of the individual adventurers, the monsters and how many hit points and experience points they're worth, and which adventurer at which time defeated which monster. We're going to use this data set a couple of times in order to try and explore what we can do within simple select statements. And so let's start off with the simplest possible select statement that I could run on this actual data. I can say, select a couple of rows. Here, notice the portion of the select, what I'm selecting, is referring to one row at a time. And the reason that I get multiple rows here is because the source data set, the source tuple space, had multiple rows. And if I want to avoid spamming my screen, I can limit the amount of data that I print to the screen. I can say limit 3. So I only get 3 rows here. And you can see each adventurer, their profession, and their species, each monster, their hit points and their experience points, and each adventurer on each date and which monster they happen to defeat on that date. Well, one thing that I could do is I could take all of those rows and I can collapse them. I can fold them in some fashion or filter them in some fashion. And a common way to do that might be a select distinct query. If you think about an SQL query as returning a bunch of tuples to you, one of the things you could do is say only return unique tuples to me. Only return tuples where we have a unique monster. And so this table here that represents which monsters were vanquished by which adventurers at which date can tell us there were 19 unique monsters that were vanquished in the running of all of these games. And so if there were 20 monsters in total, that means one of them was never beaten. Maybe that's the Balrog at the very bottom of the dungeon. I can also select distinct with 2 columns. And when I do that, what I see is this select distinct is about taking the return set that I get, which is a bunch of tuples, and giving me only the unique tuples. And so if this particular adventure happened to defeat 2 trolls, I won't see 2 rows in my result set. I'll only see 1 row. Because the select distinct is saying, oh, give me only the distinct combinations of these. What you can see is the fundamental thought process behind the select is all about returning records, returning tuples, and then doing some manipulations on those tuples, joining them together. Now, the select distinct has some additional verbiage, some additional syntax behind it. I can tell it to select distinct on a specific expression. And so here, this is selecting all of the adventurers and monsters from Who Vanquished Whom, but it's only doing the distinct on the adventure, which is why we see this Hydra appear twice. Otherwise, or actually no, the Hydra would appear only once in the previous query because the uniqueness is determined by both elements of the tuple. And so here, I guess if I select distinct on the monster, you can see no monster appears more than once, but the adventurers may appear more than once. And so this query might be very useful for me to say, give me at least one adventurer, I don't care who managed to defeat each monster. I don't care which one of it is, I don't care if it's the first one or the last one, but just give me one of each for each monster. Maybe I'm using that for some debugging for the data. I can order this data. Understand that the data itself is stored on disk in some ordering. But from my SQL perspective, I really am considering that ordering to be some projection of this data. And so I'm not usually assuming that there is a fundamental ordering to this data. There's a data layout ordering, but from my perspective of the query, I actually perform some sort of sort explicitly when I care about it. This is very different than tools like NumPy or Pandas, where the on-disk ordering of the data also corresponds to something the human being wants to do with that data. It's often the case when I have my SQL select statements that I don't really know for certain what the on-disk ordering is, nor do I care, but I care about some other projected ordering, some other ad hoc ordering that I can determine from, or I can express via this order by clause. Critically, when we look at table design later, we'll see there's two ways to think of SQL, or at least to think of how you model your tables in SQL. One of them is in terms of the correctness of the underlying facts, and the other one is in terms of allowing for the most effective querying by focusing on how the data is laid out on disk. I prefer the former because I'm often working in use cases where the data itself and the correctness of data is more important than just making analytical queries really easy to do. We'll see that later. But fundamentally, this ordering is something that we're doing as part of the querying every time we query. Now, I can do something a little bit more sophisticated than that. I can perform a function as part of my query. One thing to note is when I perform this ordering, notice this ordering has to come last. I have to decide basically the broad strokes of what I want to query. Oh, sorry. I should take a big step back. This ordering needs to order on something that was actually retrieved from disk. I don't know what the underlying disk layout of this data was. Maybe one of these columns was stored over here and this other column was stored over here. In Postgres, if you're going to order by some column, you need to include that column as part of what you're selecting, and that you can think also forces it to actually be read off of disk. And we'll see a lot of the consideration for how SQL is designed really comes down to minimizing disk reads for very large data sets. But setting that aside, when I select, I can select any number of columns, individual row values for each column, but I can also perform computations on this. So here you can see I can do a substring, and I can get the first initial of each one of these entries. And I could use that as part of my select distinct, so I could say, give me one person whose name begins with A, one person whose name begins with B, one person whose name begins with C. Now, in each one of these cases, I'm trying to reduce the spam that's coming to my screen, and so I'm doing some sort of limit 3. But I can also do offsets. I can also do pagination limits in Postgres and in later SQL standards, I think from 2008 forwards. You can also specify an offset. So give me 5 rows starting from the 900th row. So you can think if you're building some front end and you have a next page, next page, next page button, well, you can implement that very easily as long as the data doesn't change as you go between pages by just saying, oh, give me 10 rows. That's how many I see at one time. And each page corresponds to some offset from the beginning. There's even another syntax for this, offset fetch, where you can say starting from some offset fetch the next 2 rows or fetch. And you can specify this. It's not that different than the limit offset, but this is a little bit closer to how it may be implemented in other database products. Now, I've talked a lot about how we can select one row at a time. I want to talk about how we select multiple rows. The simplest way for us to do an operation on multiple rows simultaneously is to group by. The SQL group by is very different than our pandas group by. And in our pandas group by, we have an apply, a transform, and an ag, which actually correspond to multiple different things within SQL. The SQL group by is about taking that entire tuple space and partitioning it into exhaustive, non-overlapping partitions of the data. And so group by adventure says, take all of the data and then say all the adventures in this bucket, all the adventures in this bucket. That partitioning cannot overlap. That partitioning must be exhaustive for the entire data set. And, well, I guess you could have nulls and then that you don't really see them, but you get the idea. And the operation that I perform is on just that bucket as a whole. So, given this data, I could group by the adventure and the monsters. Oh no, I can't, because which monster? These are all the monsters the adventurer vanquished. Which monster would I pick? I'm looking at a group of a bunch of monsters that they defeated. Here you can see in Postgres it kicks you out if you try and perform a group by and get a single column value that you're not aggregating over. Other database products like MariaDB just give you whatever row happens to be the first one that's loaded, but Postgres is a little bit more judicious about saying, you know what, I think you're doing the wrong thing. Instead, what I might want to do is I might want to count this. And so here you can see how many monsters each adventurer happened to defeat, and we can even make this alphabetical. And there you go. And we can name this column however we want. And you can think this is some aggregate. Now, there's a very slight difference between this and this. If we do count star, that means how many rows there were. If we do count monster, it's how many non-null values were in that particular monster column. And we'll talk about null in a bit, but for the most part, they're really identical for this particular data set that does not include any nulls. If we wanted to filter the data, we could filter the data. And we could filter the data by some predicate. So here I could say, give me all the adventurers from the list of my adventurers. If the adventurer's first character of their name begins with A, B, or C. And if you want to see, we could get all the data for that adventurer, their profession, and their species as well. When I do a select where, I can also, do this a little bit more string manipulation. If I'm in Postgres, I can split this name into two parts, and I can look at just the first character, the last part. So here this would be everybody whose last name began with A, B, or C. But if I wanted to do that, I might think it might be easier to use some specific filtering syntax like the like syntax. The like syntax allows us to use these percents to indicate wildcards. So this is any row where the adventurer starts with A and then has any nonsense after it. Here, this is anything where there's an A somewhere within these, and this is anything that ends with A, and there wasn't anything that ends with A. However, in addition to this, I can also use POSIX regular expressions in Postgres. And so here, this might be closer to what I want. I want any word, or any one or more of any word characters, then an A to C, then one or more of any word characters. So this would be everybody whose last name began with A, B, or C. Bear in mind, these are not Perl-compatible regular expressions, so some of the stuff that you might want, like your look ahead and look behind, are not available. These are POSIX regular expressions. If you want something even weirder, Postgres has an SQL regular expression dialect using the similar keyword. And here you can see it's very limited. All you can do is repetition and placement and character classes. There's not a whole lot more than just that, but here you can see any A to Z, one or more of them, an A to C, and then an A to Z, one or more of them. So this is everybody whose last name began with A or C. Now, one thing that comes up quite often is, why on earth do I have a where and a having? And this speaks again to the mindset behind SQL. When I'm performing some sort of query, I might want to filter this based on some computation related to that query. So I might want to filter this based off of some computation performed on the name. And I did that before, and I did that with the where clause. If the computation I want to filter on is a row-level computation, it only needs the data from one row, I use where. If it is a grouped computation, it needs more than one row of data. It needs to first group things together, perform a computation like an aggregate, and then it comes into the end and operates. I need a having. And so here, if you see me try to find all the adventurers who defeated more than 900 monsters, this will fail. I need to make this a having clause. And so here, these are all the adventurers who defeated fewer than 900 monsters. And what you can think is the distinction between where and having is, where does it fit within the pipeline? Is it part of the row level filtering, or is it a filtering that's done on the computation once it's already grouped and once aggregates happen? There is a meaningful difference here from the perspective of how SQL may actually execute these. Remember, beyond this notion of working within tuple spaces, in SQL, what we're trying to do is we're trying to be very parsimonious about the number of disk reads that we do and how much data we load from disk. Because we don't know how large these data sets are. They may not fit into memory. And also, it's 1989, and disk is really slow. We don't have SSDs. We don't have Gen 4 M2 NVMe. We have spinning Rust, and it's like this big for 1 megabyte of disk. And so, we want to be very careful about how many disk loads we do. Well, you could think what the where clause is doing is it's first subsetting what data it has to look at to minimize the total amount of data that has to be put into this query. Whereas what the having is doing is it's saying, oh, well, I've already loaded the data, already performed some computations, well, do one other filter on it. You could think that in that having, you might do something like this, where adventurer, let's do a substring adventurer from 1 to for 1 equals A. Very strange. You can see that actually worked. But this is going to perform this computation after it's already loaded the data. This is much better done as a where because I want to be as conservative as possible in terms of the total amount of data that I'm loading. Now, the last thing that I want to talk about is the select star, which you've seen many times. So here I'm going to select a bunch of values into a temporary table. And you can see I could insert additional values in this table. And you know what? When I do the insert, I don't have to specify the columns. That's actually optional. And you could think, why would I ever want to specify the columns? Well, if I were slightly distant from the definition of this temporary table, I might want to be really careful that 135 is the num column, that GHI is the name column, and that null is my flag column. If it were the case that in the same transaction, in the same block of SQL, I created this table and then inserted something, well, I can look one line up and see exactly what those columns are. I don't need to specify what the column definitions are. In a very similar sense, if I were selecting from this table and I knew for certain what was in this table because maybe it was something that I constructed as part of my query, maybe it was in a common table expression, maybe it was in a subquery, maybe it was using that unnest trick or my select from values trick, I probably don't need to doubly specify which columns I'm selecting because they're already specified somewhere else. And this may be redundant. This may lead to some awkwardness in I have to change things in multiple places. Whereas, if either I don't care which column is which, because maybe my database adapter will give me a named tuple back, and I can just look up the columns by their name in my application code, or if within my query I know for certain what the order of the columns is because I created the thing beforehand, well, I could just do a select star. And that's generally where I would encourage you to do a select star. And so, in summary, this is what we took a look at. We looked at single row expressions, and the mindset that we've seen here is the select statement as an entity unto itself is all about performing one expression on one row at a time. If we need multiple rows, namely non-overlapping, exhaustive partitions of the dataset and grouped aggregations on those with no notion of what the order of those elements is, that's what group by is all about. The distinction between where and having is where is about filtering the data before it gets loaded, effectively performing a filtering on an individual row, which can happen really early in the process. Whereas having is about filtering on a grouped expression, which requires that you load up the data and perform the grouped expression before you can do the having. And one other thing that we saw was Postgres has a lot of really cool features. It's not 1989 anymore. This is definitely at least the year 2000.